Dear students, welcome back. Today we will look at some problems in assignment number 12. So in assignment number 12, the first 4 problems will be you can discuss with your tutors in the tutorial sessions. Then that leaves us only the 5th problem, which we will do in this session. So let's look at what is the problem. So what we are given is a second order differential equation, which is called the Legendre equation. Okay, so in the Legendre equation, what you have is for any constant p, that p appears here in the equation. So for each p, you have an equation. So once you fix a p, p is a real number. Okay, and then what you have, so this ODE is called the Legendre equation. We have not given here the domain, it doesn't matter. Ideally, if you want to solve it, we usually solve it in the region when x is minus 1, 1, but that doesn't matter. Let's not worry about that. So here, whatever we are doing here is valid in entire R except some few points, okay, that we will see during the thing. First of all, what is question number, first question 5a. 5a is asking you find all the singular points and classify them. Okay, so what are the points? So let's do A. So if you look at the ODE, which is 1, 1 minus x square y double prime minus 2x y prime plus p times p plus 1, where p is the given real number. So this is the Legendre equation, the differential equation that we are given. So what are the singular points? So you write it in the normal form. So you get this p plus 1, 1 minus x square y equal to 0. Okay, so now if you can observe, the denominator here vanishes whenever x is plus or minus 1. So except these points, every other point, so except these points, so whenever x is not equal to plus or minus 1, these are ordinary points. Right, these are ordinary points, and x not equal to plus or minus 1 is a singular point. Okay, so now we need to, so these are the singular points. So what is the classification? We have to check whether it's a regular singular point or not. So how do we check whether it's a regular singular point or not? So let's take x equal to 1, whether it's a regular singular point or not. So what we have to look at is what happens to x minus 1 of the coefficient px, which in this case is minus 2x, 1 minus x, and 1 plus x, right? This is your px, and this whether this is analytic at 1 or not. So you can actually see here that this, with this minus sign, this goes off, and at x equal to 1, what you get here is so this goes off. So what you get here is 2x by 1 plus x, right? So you get, what you get is 2x plus 1 plus x, and that's an analytic function at x equal to 1, right? There's no problem at x equal to 1 here, right? Similarly, now if you look at x and what about the second one, that is this term. So there you have to use There you have to use x minus 1 square of p plus 1 by saying 1 minus x and 1 plus x. Again, with a minus sign, you can cancel the one term here and one term here. Okay, so let's say with the minus sign here. Now this is also analytic at x equal to 1. So x equal to 1 is a regular singular point, right? X equal to 1 is a regular singular point. Okay, so the same thing will be valid for x equal to minus 1. If you take x equal to minus 1, you have to multiply by x plus 1 minus 2x 1 minus x 1 plus x, and that gives you minus 2x 1 minus x, which is analytic at x equal to minus 1. Okay, similarly for q, you can verify that the similar thing will be valid. So like that, I'm not going to do it. So you can verify that. So x equal to minus 1 is also a regular singular point. So we have classified them. Okay. Now go to the next question, B. So it says show that the Legendre equation has power series solution about ordinary point origin. So now, so origin is ordinary point, right? Because except plus or minus 1, everything else is an ordinary point. So x equal to 0 is an ordinary point. So you look at the power series solution around the origin, about the origin, right? And if you take that, then you should show that this series y1 and this series y2, where the coefficients are where these coefficients are given by this term here. Okay, these are the power series solutions of the given Legendre equation. Okay, so we have to look at about the origin. So let's look at B. Okay, so let's okay, so let's look at B. So what we need to do is start with the power series form. Okay, so let's look at the power series about the origin. So you look for a solution. Let's call it bk x power k. Okay, now you take this and you use this y, differentiate it, and so on, differentiate and use it in this ODE here. Okay, substitute for y this power series form there. Okay, if you do that, then let's remove this. I don't think we need this, right? So paper, or maybe we'll make it bigger. Yeah, that's better. Okay, so you take this y, you substitute in that ODE. Then if you substitute, then you are going to get an equation. So the equation you are going to obtain is the following. So the double derivative will give you this k plus 2, k plus 1, bk plus 2, x power k minus summation k equal to 2 to infinity k minus 1 bk x power k minus summation k equal to 1 to infinity 2k bk x power k plus summation k equal to 0 p plus 1 bk x power k, and that's equal to 0. Right? This is what you will obtain if you use the power series in the ODE. Differentiate it twice, you get this. Okay. Now we just have to rearrange because we have to equate like terms. So what we will do, so let's look at the k equal to 0 here. So there's a k equal to 2 here, k equal to 1 here, k equal to, so look at all k equal to 0 terms. So there's a k equal to 0 here, there's a k equal to 0 here. Get them out. So what you get is 2 k equal to 0, k equal to 0, k equal to 0. So it's 2 into 1. So it's 2 b2 plus from here p plus 1 times b naught. Okay, and that is the first k equal to 0 term. Now look at k equal to 1 terms. So k equal to 1 terms comes here, and comes here. So 3 such terms. So k equal to 1, which makes it 3 into 2, 6. So 6 b3 minus 2 from here, 2 b1 plus p into p plus 1, k equal to 1 is b1 times x. Right, that is a k equal to 1 term, and then the remaining term, which is plus summation k equal to 2 to infinity k plus 2 k plus 1 bk plus 2 minus k minus 1 bk minus 2k bk plus p into p plus 1 bk x power k equal to 0. So you have this series here becoming this one here. Now you equate coefficients like terms here, so that since the right hand side is 0, so what you obtain is from the first term you get b2, which is minus p plus 1 by 2 b naught. Right? Now similarly you can also from the second term here we get what is b3, right? b3 is minus p minus 1 p plus 2 by 6, okay, by 6 into b1, okay, and then the remaining terms k equal to 2 here. So for all k greater than or equal to 2, you get b k plus 2 is equal to minus times p minus k p minus k plus 1 by k plus 1 times k plus 2 of bk. Okay, so this is what you will get where for b for all k bigger than or equal to 2. So b2 is here, which depends on b0, b3 is here, which depends on b1, bk plus 2 starting from 2, which means it's starting from b4. So b4 depends on b2, which in turn depends on b0. So all even subscripts depend on b0 and all odd subscripts depend on b1. Okay, so this is the, once you match the coefficients, this is what you get. Now just for, so since we already have seen that for even something happens and for odd something happens, for instance, suppose you take k is even, that is its multiple of 2m. If k is 2m, right, then your b 2m plus 2 is going to give you minus p minus 2m p plus 2m plus 1 divided by 2m plus 1 2m plus 2 b2m. Okay, and the same thing you do for b, now for k 2m minus 1. Okay, so this is valid for all m which is natural numbers, right? So all even, so k is even, then if m is all natural, k is even. Now for 2m minus 1, so you start for all m bigger than or equal to 2. Right, because when you take m equal to 1, you are starting from 2 here, so next is 3, so you have to start from m equal to 2, so 4 minus 1, 3, that is how you start, right? So for all m greater than or equal to 2, you have b 2m minus 1 plus 2, which is plus 1, right? 2m plus 1 is minus times p minus 2m plus 1 and p plus 2m divided by 2m into 2m plus 1 and b times 2m minus 1. Okay, so this is the relation that we have for the coefficients b, right? Okay, and this b is something that starts from the power series. So if we find all b, then we have found y, right? That power series solution. So this b's have these relations. Okay, now you can also see that when we, so m greater than or equal to 2, m equal to 1, right? So in this relation, if we, instead of taking just, if you also take m equal to 0 here, k becomes 0, and if k becomes 0, it corresponds to b2, and in b2 this relation will be satisfied by this relation. So you can actually include 0 as well here, and in this case you can also include 1. So in this case you can also include 1, right? Because when you take when you take m is equal to 1, then it is 2 minus 1 is 1. Sorry, k, I mean, when m is equal to 1, it is 2 minus, 2 minus 1 is equal to 1, which is b1, and not b1, what do I want? 2m plus 1, yeah, this is true for m equal to 1, because when if I put m equal to 1, then this is b5, right, and that's valid here. We also want b, so these relation are already included in this here. So here this is for valid for all m. Okay, so now you use this information in your y of x, right? If you use that, then you can write every bk, every even subscript bk in terms of b0, and every odd subscript bk in terms of b1, right? So if you segregate those terms, you can see that you can write it as b0 1 plus c2 x square c4 x power 4 plus so on plus b1 x plus c3 x cube plus c5 x power 5 and so on, right? This is what you will get. And what are these c? Your c of, let's say, 2i is precisely b2i by b0, and your c of 2i plus 1, that is all odd c's, will be odd b's by bi, sorry, b1, not bi, b1, right? Now this is valid for all I, 1, 2, 3 and so on. Okay, so what you do here is, so whatever you have written here, let's highlight it. So whatever you have written here, this you call as y1 of x, and what you have here, this you call as y2 of x. Okay, and that's precisely what you wanted in the problem, right? You wanted y1 of x and y2 of x, and this is the relation that we have obtained. Okay, whatever we are saying here, m or k, so this is the relation that we have obtained, right? If we plug in c0 and c1 to be 1, that's what you will obtain here. Okay, so this is the relation that we have, y1 and okay, so this is the relation that we have, y1 and y2. Now you can see that from whatever we have written here, if you choose b0 to be 1 and b1 to be 0, then what happens is that all the odd indices will vanish away. What you will have is only the y1, you will have only the y1 solution. Similarly, if you choose b0 to be 0 and b1 to be 1, then what you will be left with is the y2 solution. Okay, and those are precisely the linearly independent solution that you will obtain for the Legendre equation. Okay, that is what we need to prove in B. Okay, that's what we have to prove in B. Now let's prove C. So what is C saying? C is talking about what happens to the solutions when you choose in particular P to be 0. What happens to the solution when you choose in particular P to be 1. In fact, what this theorem tells you, what this problem is trying to tell you is that once you fix the P, which is the case in the Legendre equation here, once you fix this P, you are going to get two solutions, two linearly independent solutions, and one of them will be a polynomial of degree P. Okay, and that polynomial is called the Legendre polynomial of degree P. So when P equal to 1, it's degree 1, and P equal to 0, it's Legendre polynomial of degree 0. More generally, once you fix a P, one of the solutions is going to be a polynomial of degree P, and that is called the Legendre polynomial. Okay, so let's obtain that. So at least the problem is telling you that the Legendre polynomial of degree 0 is precisely the constant function 1, and the Legendre polynomial of degree 1 is precisely the identity function, that is y equal to x function. Okay, so let's and the other solution is something else. Okay, so let's do C. So let's do C. Okay, so for C, what you do, first you start with P equal to 0. So for P equal to 0, if you look at the coefficient C2k plus 2 that we have obtained here, right? So C2k plus 2 by your formula, that whatever we have here, right? This one. Let's look at this here, right? So use this. So if you use that formula, what you get is this relation, right? 2k plus 2 and C of 2k. So the all the even indices were depending on the even things, right? Now this is valid for all k from 0, 1, 2 and so on. Okay, so if this is valid, then you can immediately see that when you put k equal to 0, 2k makes it 0, so 2k plus 2 C2 is 0, right? So if C2 is 0, C4 is 0, so every even in this even subscript of C is 0, right? Which basically means that C2k is 0 for all k bigger than or equal to 1, right? And if all ck are 0 in this formula, even indices are all 0, y1 is precisely the constant function 1, because we have chosen b0 to be 1, right? So once you choose, so y1 of x is precisely the constant function 1. This is the Legendre polynomial of degree 0. Now what happens to y2, right? So if for y2 you look at the corresponding all the odd indices of C, so you write 2k plus 1. If you use that formula which is written in terms of B, which is 2k minus 1, 2k plus 1, C of 2k minus 1. Okay, and this is valid for k equal to 1, 2, 3 and so on. Okay, so if that is valid, so now that you know all ck, you can now compute it. For if you put k equal to 1, what happens? It's 2 minus 1, 1, 1 over 1 over 3, 1 over 3 of 1 over 3 of c1, and c1 depends on b1, which is chosen to be 1, right? So if, and then similarly so from c1 you get c3, and then you get c5. So you plug in all the values of c1, c2 for all where k, you compute that. So once you compute, then you know what is the solution of y2 of x, right? Because y2 of x, you replace all odd indices of all subscripts of c, right? If you use that, you are going to get the series. Okay, this is the series that you will get. So this is your second solution, and you can see that they are linearly independent, y1 and y2. So this is your y2. Okay, but that's now a series. But in the problem, if you notice, y2 is given to be in terms of log. Now that's what is given is precisely whenever if you restrict your x in the unit such that mod x is less than 1, that is between -1 and 1, then the series that you have here is precisely equal to half times log of 1 plus x and 1 minus x, right? This you can see if you know the formula for log 1 plus x. So you see this is log a by b, which is same as log a minus log b. Log a is 1 plus x, log b is log 1 minus x, and that has an expansion. So if you sum them, some opposite sign terms get cancelled and some terms come as double, and that is what brings this half here. Okay, so for mod x equal to mod x less than 1, the series is precisely this. So this is for the case when p is equal to 0. Now let's do for the case p equal to 1. So you repeat the process. When you put p equal to 1, so in the formula there you put p equal to 1, then you get this relation for the coefficients, right? 2k minus 1, 2k plus 1, c 2k, and this is true for all k 0, 1, 2 and so on, right? Now if you use this information, put k equal to 0, you will get all the even indices c in terms of c0, which is actually 1, and if you use that in the relation of y1, the formula for y1, you will see that y1 will be 1 minus x square minus x power 4 over 3 x power 6 over 5 and so on. These are the coefficients that you will get. Again, if you restrict yourself to mod x less than 1, this is precisely 1 minus x over 2 log of 1 plus x and 1 minus x. This is precisely what is given here in the question. If you look, this is what is there. This is coming for that case. So y1 is that. Okay. So that is your y1. This is your y1 in the case when p is equal to 1, right? And when mod x is less than 1, this is what you have. Now for the case when p equal to 1, what happens to the odd subscripts? So for the odd subscripts, you will see in the same formula, you put p equal to 1 there, so the relation becomes 2k 2k minus 2 by 2k c 2k minus 1, and this is valid for k 1, 2, 3 and so on, right? Now in this case, if you notice, when you put k equal to 1, the numerator is 0, so this is 0, so which means that C3 is 0, so every odd term later is 0, so finally everything reduces to only the first term, which is y2. So in this case, what remains is C3, C5, everything will be 0, only this term will remain. V1 is chosen to be 1, so your y2 is precisely x, which is a Legendre polynomial of degree 1. Okay, so that's precisely what we had to prove in this 5c here. Okay. Okay, so with this we have completed the assignment 12, right? Assignment 12. I'll see you in the next session. Thanks a lot.